Hello student, good afternoon to all of you. Uh, you are welcome to this new video lecture. Today's video lecture is highly interesting and fantastic in the chemistry, right? So the topic of today's lecture is Kapustinskii equation. So that is used to determine lattice enthalpy of a ionic solids, right? So the Kapustinskii equation is expressed as delta HL K nu mod of Z plus mod of Z minus upon R plus R minus in bracket 1 minus D star upon R plus R minus in kilojoule per mole. So where delta HL indicates lattice enthalpy of a ionic solid, K is Kapustinskii constant. The value of this constant is 1.21 10 to the power minus 4 joule meter per mole. And nu is the K is called Kapustinskii constant. And nu is the number of ions in unit formula of ionic solid, right? So D star is the conversion factor. This is D star, which has value 3.45 into 10 to the power minus 11 meter, right? So R plus and R minus are the ionic radii of ionic solids. R plus R minus indicate ionic radii, indicate ionic radii radii of ionic compound, right? And this value indicate interionic distance. R plus R minus indicate interionic distance, right, in meter. Now this equation depends on charges Z plus and Z minus on the cations and anions. Z plus Z minus are the charges on cations and anion, right? So in this way, this Kapustinskii equation depends on number of ions in a formula unit or unit formula and charges of cation and anion and interionic distance, right? R plus plus R minus in ionic compounds. As you know that all alkali metals like lithium, sodium, potassium, rubidium, cesium and francium. So these are the alkali metals which form ionic compounds, right? All these form ionic compound, right? And ionic compound, like you can say, that is NaF, right? or Li2CO3, right? These are ionic compounds because it has Na plus and F minus, and here Li plus and carbonate as a polyanion, right? So in the ionic solids, actually cations and anions, both entity existed. So what are the real structure, what are the actual structure of the ionic compounds? If we are not able to determine experimentally, if you have only ionic radii, then we can calculate lattice enthalpy of the ionic solids, right? So suppose this ionic lattice, what is ionic lattice? Delta HL. It is the amount of energy released when 1 mole of ionic compound is formed through the combination of its constituent cation and anion in a gaseous state, right? So if there is a ionic compounds like NaCl, how it forms? Na plus in gaseous state will react with chloride ion in gaseous state. So that forms NaCl in solid state, and the energy released as delta HL. So once this ionic compound is formed through its constituent cation and anion in gaseous phase, the energy is released. This released energy is negative, right? Negative. It means if ionic compound is formed, then energy is released. Means negative. Delta HL negative, right? So this indicates the reaction is exothermic. Exothermic. Okay. In reverse, we can also define lattice enthalpy, the energy required to break up or disrupt 1 mole of ionic compound into its gaseous cation and anion is called lattice enthalpy. Reverse direction is also possible, right? So in this case, delta HL must be positive. In this case, delta HL must be negative, right? So both way it can be defined either positive or negative, right? So all the alkali metal cation actually forms ionic compounds. So what are the lattice energies of each ionic compounds? Actually through the formula we can estimate, because if you have no sufficient knowledge about the lattice structure or crystal structure, and it is very difficult to estimate experimentally, then through the application of ionic radii we can estimate lattice enthalpy of any ionic compounds, since delta H L is directly proportional to nu number of ions in a unit formula, and also it is proportional to mod of Z plus and mod of Z minus, right, and divided by interionic distance, right. It means larger the interionic distance, lower will be lattice enthalpy of ionic compound, and if number of units in a unit formula, number of ions in a unit formula is high, then lattice enthalpy will be high, and it also directly proportional to charges on the cation and anion. If higher charges on cation anions indicates the ionic compounds possess much more lattice enthalpy. So through the application of this equation, we can estimate the idea of lattice enthalpy of any ionic compounds. Suppose we have given NaCl, right? So NaCl means this ionic compound possesses Na plus and Cl minus, means Z plus is equal to plus 1 and Z minus is equal to minus 1. So actually there is a mode of Z plus and Z minus. It means there is no matter of either positive or negative. So 1 multiply 1, and number of units, number of species in unit formula, here NaCl only nu is equal to 2, right? 2 ions, actually Na plus and Cl minus, and R plus R minus is inter-ionic distance of Na plus and Cl minus. So if we have a inter-ionic distance and charges and cations and number of ions in a unit formula, then we can estimate lattice enthalpy of any ionic compounds through the application of this value. So here we are uh, uh, considering alkali metals, since alkali metals में Li, sodium, potassium, rubidium, cesium, right? So the ionic radius, ionic radius of this Li cation in a ionic phase, actually we are considering here ions. So the radius of Li plus 50 radius of Li plus 59 picometer and Na plus 102 picometer, 138 picometer, 148 picometer and 174 picometer, right? So what you have observed is that in a group from moving top to bottom, alkali metal cations from lithium to cesium plus, ionic radius always increases. Okay, so it has unit in picometer, size in picometer, right? So 1 picometer is equal to 10 to the power minus 12 meter, right? So in this way we can convert this picometer into meter. So lithium plus is the smallest size, which has 59 picometers, and cesium plus is the largest cations in the respective group, 174 picometer. Okay, 174 picometer. What you can expect about lattice enthalpy? So as you know that the distance, interionic distance increases, means this Cs plus, when it forms any compounds, it has lowest lattice enthalpy. Lattice enthalpy, because it create lower interionic distance. Okay, and once you talk about lithium plus, when it forms ionic compound, so it has highest interionic distance, so it has lowest interionic distance, so it gives lattice highest lattice enthalpy, right? So interionic distance through the Li plus should be minimum, and through the application of cesium plus cations, interionic distance is maximum. As you know that delta HL inversely proportional to R plus R minus, means larger interionic distance will produce lesser amount of lattice enthalpy in a ionic compound, right? So in this, from the this equation, we can uh, actually uh, explain about the lattice enthalpy of alkali metal ionic compounds in a first group. It means lattice enthalpy decreases. Suppose if there is a one ionic compound like LiF, right? NaF, KF, RBF, and CSF, right? So these are the ionic compounds actually. So if there is a lithium cation and fluoride anion, then the lattice enthalpy of this compound must be high, and lattice enthalpy of this cesium fluoride must be low. Lattice enthalpy low, right? And it has high lattice enthalpy. High lattice enthalpy. So in a conclusion, we can say that in a first group alkali metals, all alkali metal cation forms ionic compounds, and the lattice enthalpy of smaller alkali cations is very, very high, while larger alkali cations forms ionic compounds which has lesser lattice enthalpy because of interionic distance. Okay, so in this way we can predict the lattice enthalpy. And what is lattice enthalpy? It means that uh, if you uh, think on the lattice enthalpy, there is high lattice enthalpy. It means there is a high electrostatic interaction. Higher lattice enthalpy means higher lattice enthalpy means more electrostatic interaction between cation and anion, and reverse. Lower lattice enthalpy means there is a weak electrostatic interaction between cation and anion. Okay, so in broad sense, you can also say if there is a more electrostatic interaction, okay, if there is a more electrostatic interaction, means ionic compounds has higher melting point. So ionic compounds has higher melting point. It means lattice energy is high and ionic compound is high. Okay, in this way we can think that lattice enthalpy is uh, very important topic in the ionic solids. So that gives us idea about the uh, stability of ionic compounds, so which will be discussed in the next video. Thank you students for listening this inspiring and scientific lecture. Okay.